Hi, my name is Patrick Reagan. Part 3, OSI Model Physical Layer video will go more in depth of the physical layer. It also covers the various technologies that are used in the physical layer. Layer 1, or physical layer, deals with the physical connection between devices, including the transmission and reception of raw binary data over a communication medium. It includes, but is not limited to, cables, jacks, patch panels, punch blocks, hubs, repeaters, multi-station access units or MAUs, and network interface cards. Concepts related to the physical layer include topologies, analog versus digital, encoding, bit synchronization, baseband versus broadband, multiplexing, and serial data transfer. Network topology describes the physical and logical structure of a network, including how devices are connected and how data flows. If you can touch it, it is part of the physical layer, making this layer one of the easiest to understand. The unit of measurement used on the layer is bits. As you probably already know, a byte is a group of 8 bits, which represents 8 separate on or off settings. In data, the on-off settings are represented by 1s and 0s. In networking, the primary difference between analog and digital communications lies in the way data is represented and transmitted. Analog is a physical quantity that continuously and infinitely varies in accordance with some time-varying parameter. The physical world is analog. You look at the grass and there are many shades of green. Or you look at a red shirt and you see that many shades of red with wrinkles and shadows. When you speak, you're talking in analog waves. Analog signals are continuous waves that vary in amplitude, height of signal, frequency, number of cycles in a time frame, or phase, or offset to represent information. These signals involve sending data as continuous waves that can take any value within a range and is constantly changing. Analog signals are found in traditional telephone systems, traditional broadcast radio and television signals, analog modems that convert digital computers' data into analog signals for transmission over phone lines. Analog signals have been mostly replaced with digital signals. Digital signals represent information using discrete binary values, 0s and 1s. These signals are either in on or off state corresponding to binary values. Digital signals are less susceptible to noise and interference. Even if some interference occurs, the original data can often be reconstructed accurately due to error detection and correction mechanisms. Digital signals maintain their quality over long distances better than analog signals. This method is commonly used in computer networks and modern communication systems, including Ethernet networks, digital telephony, known as Voice over IP or VoIP, that converts voice into digital signals, and fiber optic communication systems that transmit data as light pulses. Digital devices include computers, digital telephones, network routers, switches, and modern televisions. Digital signals can be modulated into a carrier wave using various modulation techniques such as frequency shift keying, phase shift keying, and quadrature amplitude modulation. These techniques encode digital information by changing the frequency, phase, or amplitude of the carrier wave. Ethernet cables are designed to handle high-frequency signals to support high data transfer rates. Multiplexing is provided by frequency division multiplexing, or FDM, which has multiple digital signals transmitted simultaneously over the same wire by assigning each signal to a different frequency band. Each signal is modulated into a carrier frequency, allowing multiple signals to share the same transmission medium without interference. In synchronous communications, data is sent in a continuous stream with the sender and receiver synchronized by a clock signal. A clock signal is used to synchronize the timing of data transmission. The clock frequency determines the rate at which data bits are transmitted. This ensures that both parties are in sync and know exactly when data bits start and stop. Protocols that use synchronous communications often provide higher throughput and efficiency due to the continuous stream of data. In asynchronous communications, Data is sent 1 byte at a time with the start and stop bits to indicate the beginning and end of each byte. Data is sent and received at different rates, in characters or bytes, and intermittently. There is no need for clock signals to synchronize the sender and receiver. Asynchronous communication is simpler and more flexible, though it may have more overhead due to the additional start and stop bits. Synchronous and asynchronous data and signals are used in Layer 1 and Layer 2. Analog signals can degrade over time due to noise and distortion. This degradation can make the signal less clear or fuzzy. Noise can accumulate as the signal transmitted, copied, or processed. Noise can appear as hiss in audio or snow in video. Distortion can be introduced by communication channels, recording, and signal processing operations. As cable lengths increase, analog signals can lose detail and become fuzzy or grainy. If you repeat the signal so that you can get a stronger signal again, you're also repeating the distortion and noise that's been added, and if you amplify the signal, you're also amplifying the distortion and noise. Even if you try to perform signal recovery, the signal is still distorted compared to the original signal. Digital signal, unlike an analog signal, does not degrade significantly over time when transmitted or stored properly, as it maintains its discrete values and can be easily regenerated to correct for minor distortions, essentially preserving the data integrity even over long periods. Digital signals exist at specific points in time, represented by binary values, zeros and ones, unlike analog signals, which vary continuously. Digital signals can readily detect and correct errors introduced during transmission or storage, maintaining data quality. It is easy to regenerate a digital signal because the system just has to determine if the value is a 0 or 1 and resend the signal without the distortion or noise. Unlike analog signals, which can become distorted due to noise or interference, a digital signal remains largely unaffected by minor disturbances. Topology describes the appearance or layout of the network. Understanding the network topology is useful in planning a network. Understanding how a signal flows the network will help in troubleshooting problems. All physical topologies are variations of two fundamental methods of connecting devices, point-to-point and multi-point. Point-to-point topology connects two nodes directly together. In a point-to-point link, the two devices monopolize the communication medium between the two nodes. Because the medium is not shared, nothing is needed to identify the two nodes, although some implementations may use addresses. Whatever data is sent from one device is sent to the other device. Multi-point connection links three or more devices together through a single communication medium. Because multi-point connections share a common channel, each device needs a way to identify itself and the device to which it wants to send information. This method is used to identify senders and receivers is called addressing. Network cards connected on a network are identified with their physical addresses or media access control or MAC address. A bus topology looks like a line where data is sent along a single cable. A ring topology has all devices connected to one another in a closed loop. A star topology, which is the most popular, has each network device connected to a central point which acts as a multi-point connector, forming a hub and spoke. The physical layer or layer 1 devices are directly responsible for transmitting raw data bits over a physical medium such as copper wires or fiber optics cables. They include cables, connectors, hubs, repeaters, network adapters, and antennas. Question: which layer of the OSI model would you find bits of data being transmitted over a wire? Answer: physical. Question: what does a synchronous signal require? Answer: clock signal. For more information, visit these sites. In summary, Layer 1, or physical layer, deals with physical connections between devices, including the transmission and reception of raw binary data over a communication medium. In synchronous communications, data is sent in a continuous stream with the sender and receiver synchronized by a clock signal. Digital signal represents information using discrete binary values, zeros and ones. Unlike analog signals, which can become distorted due to noise or interference, a digital signal remains largely unaffected by minor disturbances. Topology describes the appearance or layout of the network. The physical layer, Layer 1, devices are directly responsible for transmitting raw data bits over a physical medium such as copper wires or fiber optics cables, and includes cables, connectors, hubs, repeaters, network adapters, and antennas. Thank you for watching this video. The next video will be Networking Concepts, Part 4, OSI Model Data Link and Network Layers. If you have not already, subscribe to the Pat Has Your Back channel. Thank you.